Okay, today we will discuss about diversity. So before discussing diversity, just want to give you a quick review about the wireless communication system model. Wireless communication system model is modeled by y is equal to hx plus n, where h is the fading coefficient and n is the noise sample at the receiver. So the fading coefficient gives you idea about the received signal power, which is given by norm of h absolute value square multiplied with the transmit power of the signal, because h is the fading coefficient and x is the transmitted signal. If you square the h, it gives you the fading power, and if you square the x, it gives you the noise signal power. So the combined uh, multiplication of h square into p gives you the received signal power, and the noise power is given by sigma n square, where sigma is the standard deviation, so sigma n square is the uh, variance of the noise. So performance of the wireless system is considered bad or worse when the noise power is more than the received signal power. This happens at constructive interference at the receiver of all the multipath components. So the overall performance of the received signal is measured by the signal to noise ratio. So signal to noise ratio gives you the ratio of the signal power or the received signal power by the noise power. So the performance is bad or worse if the received signal power is less than the noise signal power. H square into P can also be equated to equal to A square into P. A is the fading coefficient or the attenuation that gives you an idea about the combined power of the attenuation, and P is the received signal power, which is equal to x square. Now as we talked before, performance is bad when this A square P is smaller than the noise power or sigma n square. If we take P to the other side of the inequality, we get A square is less than sigma n square over P. As we know that P over sigma n square is equal to SNR, so sigma n square over P would be equal to 1 over SNR. So A square is less than 1 over SNR, or A is less than 1 over SNR, where A is the attenuation or the fading coefficient H. So this event is called the deep fade event, when the fading coefficient is less than 1 over SNR. Now A is a random variable, as we represented or presented for, which has a certain probability distribution function. We considered A square to be a Rayleigh fading component, so the distribution of A is exponential distribution given by f of capital A for random variable small a would be equal to 2 times A e to the power minus A square. So now we can find the probability of the deep fade event by this probability distribution function. So the probability of deep fade event is given by the probability when A is less than 1 over SNR, because in the brackets we put the event that we calculated before. The event here is the event of deep fade, which is A is less than 1 over SNR. So the probability of the deep fade event is given by calculating the area under the curve with the limits 0 to 1 over square root of SNR. We integrate it for this probability distribution function, which is given by 2a e to the power minus a square. If we integrate this over these limits and approximate the value of e to the power minus a square is approximately equal to 1 because a is normally less than 1, so e to the power minus a square turns out to be approximately equal to 1. If we integrate this 2a in the limit 0 to 1 over Sn under root Snr, we get 1 over Snr. This is the probability of deep fade. We calculated the BER of wireless channel to be equal to 1 over 2 SNR before, and now we calculated the probability of deep fade to be equal to 1 over SNR. So this means that the probability of deep fade is approximately equal to the BER, or otherwise BER is approximately equal to probability of deep fade. So as you can see, compared to wired systems, the probability or the performance of wireless system is poor, and this poor performance arises from the deep fade event that we calculated before, and indirectly the deep fade event is due to the destructive interference. Now, how to improve this performance of wireless systems in the probability of deep fade event? The performance can be improved with the help of a system or a method called diversity. What is diversity? Diversity can be employed to improve the performance of a wireless system through controlling or combating fading. For example, if we have a transmitter and a receiver, and we have a link between the transmitter and the receiver, if we have a single link, there is a probability which is high and depends upon SNR. The performance can be very bad, or the link can be in deep fade. If we increase these links to a multitude of values, for example as shown here that we have 4 links, then there is a probability that some of the links are not in deep fade compared to other links. For example, the first link and the fourth link are in deep fade, but the second and the third link may not be in deep fade. So what we do is we can use the diversity by sending a signal from one transmit antenna and receiving copies of the transmitted symbol ST over multiple antennas at the receiver. Here we have shown 4 links. We have one transmit antenna and 4 receive antennas. So we can receive 4 copies of the transmitted signal over the links L1, L2, L3 and L4. So if L1 and L4 are in deep fade, we can still receive information over L2 and L3. The system model of multiple antennas is shown. Antenna system is shown here. We have transmit antenna block and we have receive antenna systems here. So we can achieve nth order diversity if we have one transmit antenna and we have L receive antennas. For a single system, we have a model which is given by a scalar value of y equal to scalar h multiplied by scalar x plus a scalar noise sample value at the receiver, where x is the transmitted signal. If we have L such links, we can write equation for each input-output model. Y1 is equal to h1x plus n1. This is the model between transmit antenna 1 and receive antenna 1. Y2 is equal to h2x plus n2 gives the link or the output at the receive antenna 2, which is given by the link between transmit antenna 1 and receive antenna 2. Similarly, if we have L such antennas at the receiver, we can have output of the channel as YL is equal to HLX plus NL, where H1 is the fading coefficient of link 1, H2 is the fading coefficient of link 2, and HL is the fading coefficient of link L. So, if we combine these signals Y1 to YL and X is common and combine these signals H1 to HL, we can write the input-output model of a L-link system, multiple antenna system in a vector form as shown here, where Y hat or Y bar is given by this column vector Y1 to YL, and H bar can be given as vector H1 to HL as a column vector multiplied with the symbol X, because we are transmitting the same symbol over multiple links, and a noise vector also given by column vector containing scalars N1 to NL. So the vector notation is given by Y bar is equal to H bar into X plus N bar. Dimension of Y is given by L cross 1, dimension of H is given by L cross 1, and the dimension of N is given by L cross 1. The dimension of X is 1 cross 1 because we are sending the symbol from one transmit antennas to L receive antennas, and all those symbols are simultaneously received at the L receive antenna system. Thank you.